I'll start the class in 2 minutes. Okay, so good evening, everyone. My name is Rohan Jadhav, and I'm a PhD scholar from IIT Kharagpur, and I am the TA for the Polymer Reaction Engineering course. So this is the course NOC 24 CH55, and today is the first problem solving interactive live session for the assignment one. So I believe that assignment one lectures have already been released, and you might have gone through the lecture series. And I think assignment two also is going to be released. Either it has already been released or will be released. And for that, the corresponding interactive session will be done the next week. So we'll be doing these sessions for the entire duration of the course, and we will discuss a few problems which will help you solve your assignments, which are being uploaded on the NPTEL portal. And so we will be discussing some common concepts and problems from the polymer reaction engineering course here, and we'll try to understand what are the different problems, or any queries or any questions you have, you can ask me also, and I will try my best to possibly clear them. So starting from the very basics, since this is the first assignment and we have just started with the course itself, we have the first question here. The word polymers means many mers, parts of same or different kind, can have complex in structure and having different mechanochemical and thermal properties depending upon the monomer units attached in the main chain. So you can see right here that there are two diagrams right here where we have strong link onto the polymer chains and strong cross-link bonds. So these are different types of polymer structures which are present. The monomer is the single mer unit which forms the of whose repeating units form the polymeric chain. Now, in this case, the mer or the monomer may not be the same. Why? Because sometimes what happens is, for example, in a condensation polymerization reaction, the monomer is actually formed by a combination of two initial reactants. So those two reactants combine to give you a single monomer, and that forms your monomer for the entire polymer. So in that case, your monomer is not actually like dependent. It's not actually the same as your mer unit. That is the MER unit because for example, condensation polymerization, the initial reactants will form your monomers, and when they combine together, they will form your mer unit, which when repeated will give you the polymer. So the definition is being asked in this question: what is the polymer, and what is the meaning of it? So, as the definition itself says, polymers, many mers, or same or different kind, can have complex structures and different mechanochemical properties and thermal properties. So, this definition is true. So, here the example shows the straight chain polymer and a cross-linked polymer. The dark blue portions show the cross-linking strong bonds, which provide extra stability and mechanical properties to the polymer itself. Moving on to the next question. Which of the following is not a monomer? So it is asking what is not a single molecule. As we discussed. Hello, hello. Are you having any connection problems or something? Hello. Okay, so I will keep going with the problem now. Which of the following is not a monomer? So we have the options are ethylene, glucose, starch, and nucleotide. So we have different options right here. So you can see that ethylene is nothing but your CH2 double bond molecule. So that when it's polymerized, it forms the polyethylene. So since it is the constituent unit, it is a monomer. So that part is a monomer. Then we have the glucose, or you can call it glucose or sugar or whatever you want to call it. Glucose, it's an oligomer, which is it forms it is the monomer which forms like, when combined together, it will form your polysaccharides and all. So based on that, we have glucose as a monomer. Then we have starch. Starch is a common term for long chain for carbohydrates. So you can clearly tell from the specificity of the name itself that it is not a monomer. You can see the representation right here that monomers are like small molecules which, when combined together, will form your one large molecular polymer, which forms a chain. So ethylene will be a monomer, and when polymerized, it will give you the polyethylene chain. Glucose also, when the glucose monomers are combined together, they will give you long chain carbohydrates. And in this case, you can see starch itself. So starch is nothing but your long chain carbohydrates in that case. Nucleotide is just a term given right here. So when looking for the constituent monomer itself, starch is not a monomer, it is a polymer. So we can distinguish in that way from this, that we have to focus on the constituent monomer which and look at the polymer which it forms. Next we have the polymers which melt first time when they are heated. And during the first heating, the polymer is cured, and after that, it does not melt on reheating and degrades after that are called thermosetting polymer, thermoplastic polymer, elastomers, or fibers. So the definition is asking us that there is a type of polymer which, when it is melted once, cannot be melted again, and once it is cured, it does not change its shape, and it does not degrade or it does not melt. So what are those polymers called? So This is one of the main criteria for classifying some of the polymers which you see in your daily life. As you can see that you can take the example of polyethylene. You might have seen polyethylene bags, and if you subject them to a lot of heat, they instantly melt, and they can be molded again and again, and they melt, and the remolding can be done quite easily. And that is the reason why they are termed as the thermoplastic polymers. And thermoplastic polymers are very, very common in our life. So many of the household items are made up of thermoplastic polymers because their application is not at very high temperatures. And since not high temperatures are uh, encountered, we don't need that kind of thermal strength in that material itself. Then the next category of the material is the thermosetting polymers. Now, thermosetting polymers, as we can see right here in this example, uh, you can imagine this example that different polymer chains, different polymer chains are present. In thermosetting polymers, there is a reaction called curing. In that reaction, strong cross-linking bonds, such as these dark blue circles you can see, these dark blue circles form the cross-links or the curing. Once this curing happens, the flexibility or the movement of these individual polymer chains is inhibited. Inhibited in the sense like when you heat a polymer, these polymer chains are free to move around, which means that once you heat the polymer, it starts moving around and it becomes liquid, or you can see in a molten form. So you can heat them, and the polymer chains will start moving around in a molten form. But if you start cross-linking them and form cross-links, hi Rajiv, and so the class is going on right now, and I have already discussed the first two questions, and I'm right now on the third one. Once I finish all the questions, I'll come back to the first two questions and discuss again with you. So right now I was on the third question, that is the polymers which melt first time when they are heated, and during the first heating the polymer is cured. After that it does not melt on reheating and degrades after what they are called. So this is the main criteria for differentiating between thermosetting and thermoplastic polymers. Thermoplastic polymers are polymers which do not have cross links between their individual polymer chains, and when you heat them, the polymer chains are free to move around, and once they move around quite a bit at higher temperatures, they form the molten polymer. Whereas in thermosetting polymers, once you cure them, that is right here written as polymer is cured, they form strong cross-link bonds, such as these dark blue circles in this example right here. Once you have these cross-links, the polymer chains are restricted, and when they encounter high temperatures, they are not free to move around. And since they cannot move around, they do not melt. And since they are not melting, they will directly go to the degradation temperature, where the entire polymer will start burning. It will burn away since it is not melting. It is not changing its phase or the way it is handling temperature, it straight away goes for burn. So the definition which matches this is the thermosetting point. Elastomers are one classic example of elastomers is your natural rubber, neoprene, isoprene, or something like that. So these butadiene styrene rubbers are elastomers, as in they have elastic property. Their elastic properties are very dominant. That's why they're called elastomers. And then you have fibers, just normal fibers. So the correct answer for this question is thermosetting polymers. Next, we have which of the following statements is true regarding free radical polymerization? So we have the four options here. It involves the formation of covalent bonds between monomer units through the generation of free radicals. then it requires the presence of a catalyst to initiate the polymerization reaction. It proceeds through a step growth mechanism where monomers add to the ends of the growing polymer chains, and it is primarily used for synthesis of thermosetting polymers. So, as the name suggests itself, we have the free radical polymerization. Okay, one second. So, we have a free radical polymerization. So, as the name suggests, formation of radicals is a must. So, you can see the diagram right here. For a reaction right here, we have an initiator where the effect of UV energy is creating a radical. So, that radical, when it faces a monomer, it will start generating the lone pairs inside monomer itself. And because of that, the uh, radicalized monomer will then propagate by joining with other monomer molecules and start forming the chain itself. So, free radical polymerization will involve the formation of covalent bond between the monomers. As you can see right here, that we have a C-C bond combining with another C-C double bond C molecule and forming the covalent bonding between monomer units through the generation of free radicals. So free radicals can be generated through any process which will knock out one of the electrons and try to, make make the make a lone pair inside the free radical. And then because of that, the initiation and propagation steps are occurring. And that's why the correct answer for this question is it involves the formation of covalent bonds between monomer units through generation of free radicals. Broadly, polymerization can be classified into two categories: step growth or condensation polymerization, and chain growth or addition polymerization. Statement 1 says that the classification based on condensation addition relies on polymer composition structures, polymer composition or structure. Statement 2 says the classification based on the step chain relies on polymerization mechanisms. So we can see that the definition of these two has been asked. So we have step growth or the condensation polymerization reactions and chain growth or addition polymerization. So the example which we saw just now in the previous question, you can see right here that we have the free radical forming, and then the radicalized monomer is combining with the other monomers and it is adding on to each other. So that is growing as a chain. So in that case, this is a chain growth or addition polymerization reaction. What happens in condensation polymerization reaction is that when two of the monomers or either two reactants, when they combine together to form the monomer itself, and when that monomer is polymerized, you get a condensation product. That condensation product is water in most of the cases. And when that is generated, that kind of growth is called the condensation polymerization reaction. And that is also termed as the step growth polymerization. So we have the clear definition of what is happening right here. So the statement one is the classification is based on condensation. Addition relies on polymer composition or structure. And then statement two is the classification based on the step chain relies on polymerization mechanisms. So clearly we can see that the step chain, step step or the chain polymerization reaction is based uh, is clearly based on the mechanism of how it is proceeding forward. So both one and two in these definitions are correct because it depends on the polymer composition or structure to see if the condensation product will be water or maybe some other material or will we will have a condensation product at all or not. And based on that, we can tell that these statements one and two are correct. Which of the following options is are correct for the applications of making non-stick coating on a utensil? So we might have already seen on the household utensils, we have the non-stick tawas and non-stick pans. So what is that non-stick coating which is being put on the vessels and the tawas? So that is nothing but your polytetrafluoroethylene. And that you can see right here. That is the structure. We have other materials such as the polyester, polyethylene, HDP, and LDP, but these are very temperature sensitive and they will degrade quite readily at elevated temperatures. Whereas we have the polytetrafluoroethylene, where the carbon fluorine bond is quite strong enough to withstand high temperatures. How do you make polytetrafluoroethylene? You take your polyethylene molecule and remove all the hydrogen atoms and replace them with the fluorine atoms. So you can see that if you have HDP or LDP and then you remove all the hydrogen and replace that with fluorine, you will have a polytetrafluoroethylene polymer. And this is famously called as Teflon also. That is the industrial name for this polymer, which is used for making the non-stick coating on the utensils. Next, we have which of the following have a higher melting point? Linear polymers, branched polymers, or the cross-linked polymers. So, in linear polymers and branched polymers, usually what happens is that the chains are long enough, and in branched polymers, there is slight branching involved. As you can see right here in the previous example, HDP right here, which has been shown, is quite a long chain polymer with straight chains without any significant branching involved in that. Whereas the LDP, that is the low density polyethylene, you can see that there are small branches involved right here. You can see that there are small branches. So this branching, what what it does is it creates distance between the individual polymer chains. This distance between the individual polymer chains creates, what it does is that the hydrogen bonding between these chains is reduced. And since these chains are very farther apart now, the melting point for this material will decrease. Because if the polymer chains are close packed together, they can withstand temperature much better than when they're farther apart. Why? Because they're already farther apart, and the moment they get any more thermal energy, they will easily start flowing past each other. And because of that, the melting point is quite low. Whereas in HDP, quite close packing is involved. And because of that, the steric hindrance is reduced in quite a number of ways, and because of which the melting point is evidently high. But apart from these, we have the cross-linked polymers, where the cross-linking, as I had shown in the first example itself, the cross-linking uh, inherently inhibits all the movement of the polymer chains. So that's why they are able to withstand even higher temperatures. Because as the temperature increases, since the polymer molecules cannot move, they are like stuck together. Since they cannot move apart anyway, so they are able to withstand even more higher temperatures. Since there is no phase change involved, because the polymer layers cannot flow past each other. So the higher melting point will be involved for the cross-linked polymer. So the hierarchy will go in such a way that cross-linked polymers will have the highest melting point. Then we will have the linear polymers coming in the second position, and the third one will be the branch polymers. Next, we have what is the difference between the number average, mass average, and viscosity average molecular weight. So we have four definitions here. First one is number average molecular weight represents the average molecular weight of a polymer sample based on the number of polymer chains, while mass average molecular weight considers the weight of each polymer chain. So to explain this example in a much better way, I'll make some kind of diagram right here. So let's try to understand this with this example. So you see this box, this is a polymer. Just imagine that this is a polymer, and we know that A polymer itself will have numerous chains, numerous polymeric chains, and these chains won't be of equal length. Definitely, they won't be of equal length. They will be of varying length, and that depends. So, how do you define the number average, the mass average, and the viscosity average molecular weight in a polymer? So, first statement right here says number average molecular weight represents the average molecular weight of a polymer sample based on the number of polymer chains, while mass average molecular weight considers the weight of each polymer chain. Second statement says mass average molecular weight represents the average molecular weight of a polymer sample based on number of polymer chains, while number average is the vice versa. Viscosity average molecular weight represents the average molecular weight of polymer sample based on its flow characteristics. Or the last one is viscosity average molecular weight represents the average molecular weight based on number of polymer. So first we need to understand what are these. First we have the number average molecular weight. So consider this box right here. We have different lines here. You can assume that these lines are nothing but polymer chains. So how many polymer chains are present here? One, two, three, four, five, six, seven, and eight. So we have eight polymer chains in this box. Now, this entire polymer is consisting of eight chains. If we were to define the molecular weight of this polymer based on the number average molecular weight, how would you define this? We will be looking at the weight of the chain which is present in the maximum amount. So you can see right here, these five chains, which are shorter in length, they are present in the maximum amount. So when you are defining the weight of this polymer with respect to number average, you will be focusing on the weight of these five chains. So that's how you define the number average molecular. It depends on the average molecular weight of a polymer sample based on the number of polymer chains. So the number of the polymer chains involved. So how many number of polymer chains are involved? Average of that would be giving you the number average molecular weight. Now next we have the mass average molecular weight involved. Now what happens in the mass average molecular weight is that mass average molecular weight considers the weight of each polymer chain. Now in that scenario, the first three polymer chains have the highest weight. Why? Because look at them. They are practically double in length of the smaller ones. So these three have very high molecular weight. And if you were to quantify the polymer based on the molecular weight of the mass itself, like the mass average molecular weight, you will be focusing on the weight of these three chains because they constitute the heavier part of the polymer. So your mass average will be dependent on this. So by that definition, mass average molecular weight is always higher than the number average molecular weight. So we can define and we can find out the correct option from amongst these. Hello, Raji. My voice is audible, right?
Yes, sir.
Yeah.
Some voice will be problem in the beginning. Now it is okay.
Okay. That's fine. So we have that's how you define the number average, mass average, and viscosity average of the molecular weights. So we still have viscosity average left. Viscosity average molecular weight, to understand that, we need to know about the solubility of the polymer. So there are different solvents available which can dissolve different polymers. So let's take example of this polymer itself. If we were to dissolve this polymer in a particular solvent, we need to know first how well that solvent can dissolve this polymer. There are different categories of the solvents themselves based on which it's based on how well they are able to dissolve the specific polymer. And the viscosity viscosity increase of the polymer solvent mixture is how you define the viscosity average molecular. So that definition is not present right here in these four options. So we need to go for the number average and mass average. So you can clearly see that statement one is the correct answer, where it is defined as number average weight represents average molecular weight of polymer sample based on number of polymer chains, while mass average presents the weight of each polymer chain. So first option is the right one. Next one we have, which of the following statements is true regarding gel permeation chromatography, GPC? GPC is a technique used to determine the molecular weight distribution of a polymer sample. GPC relies on the separation of polymer chains based on their chemical composition. GPC is primarily used for analysis of inorganic compounds. GPC measures the viscosity of a polymer sample to determine its molecular weight. So, which of the following statements is true? So, here is a depiction of the gel permeation chromatography. You can see right here we have a packed column and we have sample passing through it. So usually in gel permeation chromatography, you have a packed column which is filled with gel beads. These small beads, or you can call it porous packing itself. This porous packing has small pores which are used for, which are basically present so that the polymer molecules can go through them. Okay. So what happens in this is we have a column right here. You insert your polymer molecule on top, and as it is traveling, we already know that polymer molecules or the polymer itself does not have chains of equal length. If you have an extremely long chain, it is not able to enter the small pores of these gel beads. So the long chains, they go outside the beads and they come out first. So the larger polymer molecules or the larger chains exit first. Whereas the small polymer chains, what happens to them is that they go through all the small pores present inside the gel and they have to cross the entire bed. This entire porous packing they have to cross and then their signal is detected. So the retention time for them is quite higher. You can also call it a residence time. You can take it in a definition of residence time that when the polymer molecules enter from the top, the larger molecules will bypass the pores and it will go down and you will have a smaller residence time, whereas the smaller chains will have a larger residence time and they will be coming out later at a later stage. So you can see right here in the chromatogram, there are two peaks involved here. First peak is for the red molecules, second peak is for the green molecules. So from the image itself, you can see that the red molecules are quite big in the green ones. So by the definition which I just explained, you can clearly understand that the bigger molecules are able to bypass all the small pores and they are able to come out first with a lower residence time. Whereas the smaller molecules pass through all the pores and they come out at a later time. So because of this, you will be able to know the entire polymer chain distribution present inside the polymer. And because of that, option one, GPC is a technique used to determine the molecular weight distribution of a polymer sample. It is correct. GPC relies on separation of polymer chains based on their chemical composition is false because there is no chemical reaction being involved here. It is primarily used for analysis of inorganic compounds is also false because polymer molecules are being measured right here. And then we have GPC measures the viscosity of a polymer sample to determine its molecular weight. Measurement of viscosity is not being done here, but definitely the viscosity of the polymer solvent mixture should be quite dilute so that it is able to pass through the porous bed, or else if the polymer solvent mixture is quite thick, it might get stuck inside the column itself and you might get some error in your results. So that's how the gel formation chromatography works. Next question we have. Choose the correct option for the following statements. Statement 1. The polymer molecules are attached to each other with the primary and secondary bonding forces, such as covalent bond, ionic bond, hydrogen bond, and van der Waals forces, etc. Statement 2, a covalent bond forms when the difference between the electronegativities of two atoms is so small for an electron transfer to occur to form ions. So we can see right here that in a polymer molecule, the main forces which are involved in forming the polymer molecule itself are two. First is the intramolecular forces, and the second is the intermolecular forces. The first one exists between the polymer backbone material itself. Now, what is the meaning of a polymer backbone? Let's take an example of the polytetrafluoroethylene itself. So you can see that the C-C-C bond, this center bonding, that is the C attached to C, carbon attached to carbon, that is called the polymer backbone. Why is it called the backbone? Because it is the one which is carrying the entire polymer. Okay, that is the main constituent of your polymer. So that itself is formed by covalent bond because we all know that carbon can create covalent bonds because of the minute difference in the electronegativities. They are able to share the electrons quite easily, and that's why carbon is able to form the covalent bond. And then comes the secondary forces such as the hydrogen bond, which was shown right here. You can see that in two chains, between two chains, if you have hydrogen attached to them on the either side, they will be bonding together, which will be a slightly weaker force. And then we have the ionic bonds also, and the van der Waals forces, which can exist between two chains in any given polymer. So statement one is true. Statement two, when you see it, the covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form the ions. So that's exactly how the carbon is forming right here. You can see the covalent bonding forming, and that's how the covalent bond between the polymer molecule backbone is formed. Statement one and statement two are. Now, I think the last question is for polydispersity index, which statement is or are correct? Now we need to know what is the definition of polydispersity index. How do you define the polydispersity of a polymer? I would say? So we have the definition for the number average and mass average molecular weights. We already know that number average is defined based on the number of polymer chains, and mass average is defined based on the mass or the weight of the individual polymer chains. So the ratio of the mass average or the weight average molecular weight divided by the number average molecular weight will give you the polydispersity index of a polymer chain. Why is this ratio so important? Now, from common definition, we can see that the weight average molecular weight or the mass average molecular weight will always be higher than number average molecular weight because it is very difficult to form because the it is very difficult to form polymer chains of equal length. And if you are able to form a perfect polymer where all chain lengths are equal, their number average and mass average will basically be same, and your ratio will become 1. So that's why you can see that the second option, it is usually 1 for monodisperse polymer, and that is for the ideal case scenario. If your polymer, if you are using also like if you are able to maintain perfect conditions and all the polymerization processes occur in a perfect manner, you will be able to achieve monodispersity in your polymer mixture. That is, the weight average and number average molecular weight will be equal to 1. But that is not the case for actual polymers since it is impossible to achieve that kind of monodispersity. That's why it is usually 1 for monodisperse polymers and greater than 1 for actual polymers, since the weight average molecular weight of an actual polymer is always higher than the number average. Then we have it is used as a measure of broadness for the molecular weight distribution. So you can see right here in the gel permeation chromatograph, the chromatogram you are able to see, and you can see that if we were to, scale together all these different residence times together and draw a curve, what we will see is uh, we will see that it is forming a bell-shaped curve. So, for example, like this, if on the what should I say, the x-axis we have the molecular weight, what we can see is the curve goes up this way. So, in the middle, we will be having the number average molecular weight, and next to that, we will be having the weight average molecular. So, we have the number average that is M, and we have the weight average, or you can call it the mass average also, MW. So what do we get in this distribution is that the ratio of these two, if it was, you know, a monodisperse polymer, these both will coincide and your distribution will look something like this. Why? Because both of them are coinciding. Your polymer or perfect polymer will look something like this. But that is not possible. Actual polymers look something like this. Mn and Mw are quite far apart, and the ratio of these two, that is Mw by Mn, will give you the polydispersity index, which defines the broadness of your distribution. Broadness in the sense like this one. It will define the broadness of your distribution. This broadness of the distribution can tell the person who is working with it that what are the variations, or what is the mass distribution of the entire polymer itself. So it is used as a measure of broadness for molecular distribution. It is usually one for monodisperse and more than one for actual. It is the ratio of weight average to number average. Then we have the polymer with the number average molecular weight alone, with considering polydispersity may mislead. Correct. That is true. So all of the statements are correct basically for the polymer polydispersity index. So I think some of you have joined late, so I will start explaining once more from the beginning, just so that you can go through with the questions which we were discussing in the beginning of the class. So if you have any doubts, you can ask me also. It's fine. I'll just quickly go through with all of them. So, first question was the very basic about what is polymer. The word polymers means many mers of different or same kind, and can be complex in nature. Uh, that is the structure, and can have different mechanochemical and thermal properties depending upon the monomer units attached in the main chain. So that is the basic definition of a polymer, and this is true. So here is an example of the monomers where the strong link into the polymer chains are formed. And then we have a cross-linked polymer. Next, we have which of the following is not a monomer. So we have ethylene, glucose, starch, and nucleotide. So here we can clearly see that we can eliminate nucleotide from this basically. And we can see ethylene being the monomer for the polyethylene polymer is a monomer. Next, we have the glucose. Glucose also is a monomer for, you can say, long chain carbohydrates. And then we have the starch, which is a long chain carbohydrate itself. So that's why it is not a monomer. So we have starch. And then next question we have the polymers which melt first and when they are heated. And during the first heating, the polymer is cured, and after that, it does not melt. On reheating and degrade after that are called what? So we have the from definition, we have thermosetting polymers, thermoplastic polymers, elastomers, and fibers. So as I explained, that when you provide heat to the polymer chains slide past each other as the temperature increases, and they form the molten polymer, where the entire sample is molten. But in thermosetting polymers, As you can see in this slide, there is a cross-linking bond. And because of this cross-linking bond right here, the polymer chains are restricted to move around. And even if you increase the temperature, they won't move around and go to the molten state. They will directly go to the degradation state. And that will create the burnt polymer, or it will basically destroy a polymer. So that's why these polymers are called the thermosetting polymers. And thermoplastic polymers are the ones which are easily molten and can be remolded again and again through multiple heating cycles. Which of the following statements is true regarding the free radical polymerization? So, as the name suggests, free radical polymerization will require you to have a radical formation strategy first of all, and then that radical which is formed will initiate the monomer in itself. We have the ethylene monomer right here, and that clean monomer, when it starts propagating and combining with the other monomers to form its straight chain, is called the free radical polymerization reaction. So the option one, that it involves the formation of covalent bonds between the monomer units through generation of free radicals, is the free radical polymerization reaction. So this example right here, which has been given here, is of the free radical polymerization, which where there are initiation, propagation, and termination, the basic polymerization steps. Next, we have broad polymerization can be classified into two categories: step growth or condensation polymerization, and chain growth or addition polymerization. And the statements based on that definition is classification based on condensation, addition relies on polymer composition or structure. So that is true that to have a condensation polymerization reaction, you need to have a condensate form. Basically, that is the H2O, which separates out during the polymerization reaction. But for the H2O to separate out, you need to know what kind of polymer composition or structure your polymer has and what kind of polymerization reaction it undergoes. Next, we have the classification based on step chain relies on the polymerization mechanisms. That is also true. The mechanism which we just saw here is the free radical polymerization or the chain growth polymerization, you can call it. And step growth polymerization or condensation polymerization is based on the mechanism in itself. Which of the following options is correct for the applications of making non-stick coating on utensils? So we have polyester, polyethylene, HDP, LDPE, and polytetrafluoroethylene. So the common name for the non-stick coating on utensils is called the Teflon. And you can see right here the structure for Teflon, or the chemical name for it is polytetrafluoroethylene. How is that formed? You take the polyethylene molecule and replace all the hydrogen with fluorine atoms, and you will have the polytetrafluoroethylene present. Then we have the HDPE and LDPE, which are like which cannot withstand that much of high temperature, and that's why are not used for non-stick coating on utensils. Next, we have which of the following have a higher melting point. Like I said in the previous example about the thermosetting and thermoplastic polymers, cross-linked polymers or the thermosetting polymers will definitely have the highest melting point. Now, among the linear polymers or the branch polymers, you can see the example right here. In HDPE, we have white straight chains, and then in LDPE, we have some branching right here. Because of this branching, the distance between two polymer chains is quite high enough. And because of this, if you supply even a small bit of temperature, it is very easy for the individual polymer chains to slide past each other. Whereas in HDPE, since there is extremely close packing involved, it can withstand pretty high temperatures when compared to LDPE. So the hierarchy or the ranking of the higher melting points is based on cross-linked polymers will be first. Then we have the linear polymers, and then we have the branch polymers. Then the basis of definition of the number average, mass average, and viscosity average molecular weight. So from the example which I gave right here, we have few polymer chains involved. And if you want to represent the number average molecular weight, we'll be looking at the molecular weight of the chain which is repeating the most number of times. That's how you get the number average molecular weight. And then mass average will be defined on the chains which will have the heaviest weight. That is the first three chains. And viscosity average molecular weight is defined based on the polymer solvent viscosity and how that is affected. The that is affecting the measurement of viscosity and the molecular weight of the polymer itself. Then we have the gel permeation chromatography. It's a technique used for determining the molecular weight distribution of a polymer sample. We have a gel bead packed polymer column where it is having small pores inside it. It's quite porous in nature. And if you have a polymer and when you pass it through the column itself, the larger molecules, they are not able to enter into the polymer chains. They are not able to enter into the polymer chains itself. Sorry, they are not able to enter the porous pores of the packing, and then they pass on the outside and come first in the chromatogram, and in the second position, the all the smaller polymer chains come through, as they have to pass through all the pores present. Next, we have the choose the correct option. The polymer molecules are attached to. Yes, Prashant, you want to ask something?
Yes, sir. Just in gel permeation, what I understand that
Hmm.
the higher molecular weight having some kind of gravity thing that they push the gel particles inside and they go first, and the smaller one don't have that much power, so they just pass through the pores. Is it like that?
No, actually, gravity does not have a role to play here. The representation is showing it like this, that it's coming from top and coming at bottom, but it's not like that. The uh, column can be arranged in any way. It's just that the flow rate of the polymer solvent mixture which is coming inside depends. Uh, it tells you how the polymer will pass through at what rate. But the larger molecules or the larger chains, they will not be able to enter the pores of the packing. And since they are not able to enter, they will just flow on the outside and come out first. So you can see in the example also, the red beads are larger in nature, so they are not able to enter the pores itself and they will come out first. So the first peak which is observed right here is the larger polymer chains. And the second is the smaller polymer molecules which enter the pores and their residence time is higher than the previous one. So they come later. It's like that.
So like that, the bigger molecular they just pass through the annular space,
Hmm.
but the smaller one
Exactly.
pass through the pores. Is
Yeah.
it I'm getting right? Okay. Okay.
Yeah. Yeah. That's correct. That's correct. Exactly. So that's how it happens. You're right. Then we have the polymer molecules are attached to each other with primary and secondary bonding forces such as covalent bond, ionic bond, hydrogen bonding, and van der Waals forces. So we know that the polymer backbone is usually formed with the covalent bonding, and the subsequent bond orders are ionic bonds, hydrogen bonds, and van der Waals forces which exist between the polymer molecules. So we have an example right here. We have a chain and we have the hydrogen molecules present on either side. And we can see that the individual chains are being attracted towards each other because of the hydrogen present. You can see the dotted lines which are created by the hydrogen bond. And the second one is the covalent bond forms when difference between the electronegativities of two atoms is too small for an electron transfer to occur to form the ions. So you can see right here, carbon is readily able to form the covalent bonding, which forms the backbone for the polymers. Then what is polydispersity index? We have already seen the definition of the number average and the mass average molecular weights. So the ratio of the weight average molecular weight to the number average molecular weight is what defines the polydispersity index. It usually tells you the broadness of the molecular weight distribution, the bell curve, which is being shown right here. So based on that, the polydispersity index is defined, and it is usually 1 for monodispersed polymers or greater than 1 for the actual polymers. the polymers. It usually tells you, or anyone working with the polymer, that like uh, how the properties of this polymer might be changing, or what might be the reason for the results, or whatever testing which you are doing. Polymer molecular weight is a very important parameter. So I think I have discussed and gone through like all the questions. So this was only the first class. So good to see you all, that you have all participated today. And for the next upcoming weeks, we'll be going through different questions, which will be helping you to solve your assignments one and subsequent assignments. So yeah, if you have any doubts, or you want to ask anything, you can ask.
Sir, dispersion index is